Welcome back, everyone. So let's go back to where we were. So we have theorem to 3.5. Theorem 3.5 says for any elements A and B of a ring R. First of all, we have the following. Have A times 0R is equal to 0R, which is equal to 0R times A. In particular, zero R times the identity of addition with respect to the ring R is equal to that identity. And the second thing is that A times minus B is equal to minus AB, and minus A times B is equal to minus AB, and 3 minus A is equal to A. 4 minus A plus B is equal to minus A plus minus B. 5 minus A minus B is equal to minus A plus B. And then 6 minus A times minus B is equal to AB. Okay, so let's go see what's going on. So first of all, first one is since 0R plus 0R is equal to 0R. So by the distributive law, we have the following. We have A times 0R plus A times 0R, which is equal to A times 0R plus 0R, which is equal to A times 0R. So then we have this is equal to A times 0R plus 0R. So by the cancellation property, we get that A 0R times A is equal to 0R. Therefore, A times 0R is equal to 0R. Okay. Let me just get a sip of tea. Alright. So, for the second property, what we want to show is that we want to show that A times minus B is equal to minus AB. So we just write AB plus A times minus B. This is the same thing as A times B plus minus B, which is A times 0R. So that is equal to 0R. And indeed, we get that minus AB is equal to A times minus B. And by before, the answer is unique by earlier reasoning. So, and also by a similar reasoning, we get that minus A times B is equal to minus AB. So let's go on to part 3. So minus A is the unique solution of minus A plus x, which is equal to 0, or because you have minus A plus minus A, which is equal to minus A times 1 minus 1, which is equal to minus A times 0r, which is 0r. So indeed, it is the solution. So let's go on to part 4. Okay. So part 4. Minus A plus B minus A plus B is a unique solution of A plus B plus x, which is equal to 0r. But we have minus A plus minus B is also a solution. Why is that? Just because we can use the associative property again. Plus minus A plus minus B, which is equal to A plus minus A plus B plus minus B, which is 0 by earlier work. So therefore, minus A plus B is equal to minus A plus minus B. Let's go to part 5. Minus A minus B. This is the same thing as minus A plus minus B. And this is the same thing as minus A plus minus B, which is equal to minus A plus B. So we get our result. So let's do part 6. Minus A times minus B. This is equal to minus A times minus B, which is equal to minus A times B, which is equal to AB. Let's prove the last part. Minus 1 times A is equal to minus A. Okay. Minus 1 times R times A. This is equal to minus 1 R times A, which is equal to minus A, which is minus A. And we're done. So let's continue off where we left off, is that sometimes we have exponent notation for addition and as well as multiplication. So we can define like multiplicative exponents, and how we can define it is as follows. If R is a ring, and A is in R, and N is a positive integer, we define A to the power of N as being A multiplied by A multiplied by A n times. Okay. So how we can verify that A n is equal to AM plus N by using either direct property, or we could also use induction. And also AM raised to the power of N, this is AMN. And we define, so if R has an identity for any A belonging to R and positive integers M and N, then A raised to the M times A raised to the N, this is A raised to the M plus N, and A to the M to the N is equal to AMN, as I wrote before. And we can also define A to the 0 to be the multiplicative identity. Okay. We can also define multiples for a number. So n times a. This is a repeated n times. And we finally define zero times a. This is the integer, not the integer, the additive identity, 0 or. Okay. And with this we are done. So in the next couple of subsections, we will touch on a couple of things, including if every finite integral domain is a field. So I'll see you guys in the next video. Bye.